Hello everybody. Today we're going to be going over double and triple integral application problems. So we're going to have two scenarios and we are going to need to solve a problem using doubles and triple integrals. So let's start off with this first one where a mayor of a town has a plaza outside of the town hall and he wants to lay a dividing garden bed that divides, of course, the place in two, and he wants to make it in this little lens type shape, bounded by the curves y equals root x and y equals x squared. And the architects and the gardeners that are working on the project need to know how much grass are they going to need so that they can plant the flowers. So let's look at the math on this. So here we have a distance of 1 mile, 0 to 1, right? Our plot is a square. So we have to, when we're looking at the area of this thing, when we're talking about x specifically on the x-axis, we're talking about from 0 miles to 1 mile, which is the full distance of this. And then the area we care about, which is in between these two curves, the x squared is on the bottom, so it goes from x squared all the way up to root x. And it's not a number because, as you can see here, a distance from earlier, right here, would be different than a distance from all the way up here or in the middle. So these are our two parameters for the integral. So now we can just turn that into the integral from 0 to 1, integral from x squared to root x of dy dx. And then this is equal to the area. Now all we need to do is solve the first part. So the first part, you simply take the integral of dy, which is equal to y, and then you plug in, obviously, your parameters, and then you get this, which is simply the top minus the bottom function. And then what you're going to do, you are also going to do the 0 to 1 integral of this one right here. Simply go over here, 2/3 x to the 3/2 minus 1/3 x cubed. Plug in from 0 to 1. You get 2/3 minus 1/3, which is 1/3 square miles. So that means you need 0.33 square miles of grass to fill in this garden. So a considerable project. Now let's move on to, I'd say, the more interesting example with triple integrals. So here we have a pizza oven that is a square pyramid, and it has a temperature function of x plus y plus z, and it has dimensions of 2 feet by 2 feet, and its pyramid top is as shown, of course, typical of the pyramid. So we want to find out what is the heat content of the pizza oven. How much heat does it accumulate? So let's look at it. So the way to do this is we look at its volume, because it is a 3D object, and we have to analyze how the heat is changing in all three directions. So we have the integral from 0 to 2 for two of them. This is the green one happening to be the x, and then the red one is going to be the y, because they are 2 feet. They're both 2 feet. And then this is from 0 to z, which is the top right here, because this is the height of the pyramid. So we've taken into account all parameters. We've taken into account length, width, and height. And then we just have our temperature function here, and then we have, of course, our parameters dz, dy, dx, as usual when we're taking integrals. So the first step here, I'd say you could do this all at once. However, it's going to be very difficult to do this all at once. It's going to get pretty messy. So if we can just split it into this series of integrals of x plus this series of integrals y, and then plus this series of integrals z, then we can do each one individually. So I'll do one each individually for you right here. So we just have the integral over our furnace of just x, which if we put, obviously we put z in there. I haven't written it out explicitly, but this is that 2 minus x over 2 minus y over 2. And so now we just have two integrals now from 0 to 2 and 0 to 2 of x, z, dy, dx. And then after solving this one, you'll get the integral of 0 to 2 of x times 3 minus x. So now it simplifies even further. Obviously, I don't need to do the math on this, but you can figure this out for yourself. And then, of course, we take this integral, plug in from 0 to 2, and we get 10/3. 10/3 is not our final answer. It's actually one of 3 steps that we need to take. So number 2, since it is symmetrical, it's the same as the x, that means it is also 10/3. So pretty simple there, just because it's the same length. And I did not put a graphic for step 3. However, we can just look at it if we have this triple integral and we're talking about z exclusively, it will simplify down very nicely and we're going to get 8/3. So when we look at our final answer, we have t equals our 10/3 plus our 10/3, that's our x and y, and then our z is 8/3, and you can compute this on your own if you have time. And we're going to get 28/3 units of heat. Now, let's apply this in a more practical situation. Let's say we have a yummy pizza, and it is a frozen pizza, or it's a cold pizza. It weighs about 0.5 kilograms, and we want to see how long it'll take to cook this pizza in this specific oven. This oven is 200 watts, and our ideal temperature for it to be done is 90 degrees Celsius. So what we're going to do is we're going to use chemistry, so Q equals MC delta T. Our heat capacity of the dough and cheese is around 3. If the pepperonis were there, it would be a little bit more, but not considerably different. And then, so now all we need to do to compute how much energy we need to cook the pizza to 90 degrees from 5 is 0.5 times 3 times 90 minus 5, which is 127.5 kilojoules. And our time is going to be how much is actually needed versus how much is being supplied. So we need 127,500 joules of energy, but our input, because of 200 watts, is 200 joules per second, which means that if you do the math here, you get that it takes 10 minutes and 36 seconds to cook this pizza to well doneness. Anyway, I hope you liked this video, and goodbye.